Okay, the good news is we should be live. The bad news is Microsoft Whiteboard decided that today is a bad day to work, so I don't know if we'll have diagramming software today. Other than that, we should be live. Can somebody post in chat as per usual that the audio and video work? Don't know what is up with this. I'm killing the app. Wait, why does this thing have sleep mode on? What? Dear God, what is even happening here? Alright, let me check the stream status. Okay. Okay, cool. Thank you. Okay, yes, Microsoft Whiteboard decided that it is time to work. Cool. It looks like, yeah, okay, whatever. Something was not working, but now it should be. Okay. We will start in the, no, definitely something is wrong with. Okay, so pencil doesn't work. Apple, what is happening today? Oh, it's because, okay. All right. Okay, yes, yes. Everything is working. Okay. Okay. All right, let me get some water and I'll be right back and we'll start. Okay, so the goal for today, or what we are going to be working on today, I don't know how much time it will take, so I don't know if we're going to fit it all in one stream or if we will need future streams. The goal is to improve the culling code that we use. So the first most important and really like 90% of the goal is to implement cluster culling or cluster occlusion culling or meshlet occlusion culling or whatever you want to call it, which we don't have right now. If things go well and if we get it working, then I have one idea around sort of cluster occlusion culling specifically that I want to try, and also there is some cleanup on, or some small improvements I should say, on the culling code that we wrote last stream. But we'll see how it goes. I have never, as is usual on these streams, I've never like implemented the thing that I'm about to do. Sometimes it goes well, sometimes it doesn't go well. We'll see. But what is the sort of high level idea? So we talked about this on last stream, but in our pipeline, really in any pipeline, there's a few forms of culling, and you get to pick sort of what level they happen at, right? Where we are right now. Speaking of which, let's all right, I will have to hold on. There's a magic line. Okay, this is the magic line, I think. Okay. Wait. Something is weird. Hold on. What? Things have changed since the last time I ran this. What is even going on? Hold on. 1 second. First, we were getting a validation error about the this stream is off to a great start. We're getting a validation error about an extension that we're not using. I guess it's like a warning. Something is up with the shader compilation. Okay, let's ignore this. There's a more interesting, fun thing. What happened? Basically, where we were last time is that the mesh shading pipeline was still slower. And when we are today is it's faster. But there's no reason for it to be faster. What? Alright, we will excuse this brief interruption. I'm just baffled a little bit as to what the heck is happening here. Alright, something happened with our graphics driver. I don't think I rebuilt it, but it's now slow. In the original pipeline, which we don't really care about. We only care about mesh shaders for now, but this is just baffling to me. I don't think I changed anything. This validation error is sus because did I install the SDK? Oh, I did. I probably did Ubuntu package upgrade at some point. So maybe the Vulkan SDK version. So the validation error could be explained by the fact that we're using a newer Vulkan SDK, which could be because at some point the package got upgraded and I just didn't notice. Okay. The driver thing is weird because we're using a local builder. Okay, whatever. Let's ignore this. It's a problem for another day. So I was saying, I don't know what this fragment shader thing is about. We might need to look into this after we do the main portion of the stream. Okay. So there's a few ways. That you can reject triangles, and for every kind of way that reject triangles, as in remove triangles from rasterization if you know that they are not contributing to the final picture. And for every one of them, you can choose kind of which level you do them at. So we have right now 3 levels. As of last stream, we used to have only 2. Drawcall, Meshlet, and triangle. So we didn't used to do triangle before, now we do. At the same time, you can do backface culling. You can do frustum culling. You can do occlusion culling. And you can do what's called small primitive culling, which essentially is referring to culling away triangles that don't result in pixels because they're too small to intersect any center of the pixel. We discussed all of this last time. So where we are right now. Backface culling for a draw call is kind of like when you say backface culling or whatever version of culling for any given sort of granularity, you're essentially saying all of the triangles in this group don't need to be rendered because they failed this test. So backface culling for a draw call is kind of meaningless. Like, you can do this in theory. There's even cases where it's valuable sometimes for terrain rendering, but we are not doing that and we don't really plan to. We do frustum culling for draw calls. We do occlusion culling for draw calls. We don't do small primitive culling for draw calls, even though in theory it's possible. Instead, we just do level of detail, and the result of this is we don't really have small primitive draw calls. So then we now do, or we always did, like from a while back, we did backface culling for meshlets. This is called cone culling. As of last time, we do frustum culling for meshlets. We didn't used to do it before. We do not do small primitive culling for meshlets. It's possible to do. I don't know if it's viable, like profitable, right? As in, as we discussed last time, whenever you can do everything at a triangle level and get perfect results in terms of the number of triangles, so like efficiency, but it results in a lot of work that you have to spend to be able to do these culling checks. And so for every check, you have to ask, can I pull it at a higher level so that it reduces the work at a lower level? Anyway, so for the triangles, we, as of last stream, we do backface culling. We do not do frustum culling. This is a explicit choice, like conscious choice, which we made because we implemented frustum culling on the meshlet level. And it's basically perfect. It's like close to it rejects most of the triangles that are out of frustum anyway, so we don't need to do this. And we, as of last time, we do small primitive culling on the triangle level, which works great. So let's look at this table, right? There's a bunch of empty rows. So backface culling for draws, I just think for us, for our code base, I just don't think we'll ever do that. Small primitive for draws, it's in theory it can be profitable. I many years ago, like 12 years ago, I had a SPU based rendering pipeline where I did occlusion and small primitive and frustum on the draw call level. So like you can do that. I don't think we'll do this, but let's leave this for now. Like, it's possible, it can be beneficial. It's just we don't do this right now. And then triangle culling, frustum. So frustum culling for triangles we can do, is just not very profitable. So I don't think we'll realistically do this. Occlusion culling for triangles, it can just be expensive because occlusion culling requires looking up the occlusion kind of data structures. And it could be worth it, but the goal for today is to put an X here and to put a check mark here so that we don't have to think about occlusion culling for triangles, hopefully. And then small primitive culling for meshlets and draw calls maybe at some point in the future stream. It's easy to do. It's just work, right? And like, do we need to do this? I don't know. So to implement occlusion culling for meshlets, we are going to use the same structure that we are already using for draw calls. What we are using for draw calls is I don't know if you can see this, but we have this mode that visualizes the pyramid. So the way this works, it's hard to see, at least on my screen, but the way this works is that we take the depth buffer and then we downsample it to some resolution, and then we build a MIP chain for that. And then for every MIP level, the value of the pixel is the conservative estimate of the depth in these pixels. So like whatever's the furthest, I guess. Like if you have 3 pixels, and yeah, you take whatever is the furthest from the camera, and then you record the depth. That way, if an object is kind of covered by the representation of that pixel in view space from the occlusion perspective, then you know that it's a conservative test, because every other original pixel in the pyramid, in the source depth data rather, is closer to the camera in that like sort of footprint. So we went over all of this when we did the original frustum culling occlusion culling implementation like 3 years ago. I don't know which stream it is, but some stream. We can look at the so we did this over 2 streams. If you want a refresher, 13 and 14 sort of days or videos are that, and they are up on YouTube. Now, the reason why this works for us, as in the version of occlusion culling that we've implemented is conservative, meaning it should never reject objects that should be contributing pixels to screen. And the reason why that is the case is that we do this in 2 passes. So, and this is what most of the complexity today is going to be about, probably. So the first pass is we render visible objects. What does visible mean? Visible means they were visible in the past. So previous frame. This is a conservative estimate in the sense that maybe the object was visible, like, I guess it's both. The object could be visible on the last frame but invisible now, or it could be vice versa, we don't know. So this is a subset of the objects. It's possible that we render some objects that we actually shouldn't be rendering because they're now actually invisible, but we don't know, right? So we render some number of objects that are visible on screen, that were visible last time on screen. So then we built the depth pyramid. And then pyramid. And then we render all objects, or all with an asterisk, again, while doing occlusion tests using the depth pyramid. So we don't render objects that we have already rendered in point 1, but we do render objects that we haven't rendered in point 1 if they pass the occlusion test. But also in general, in the phase 3, the other thing that happens is it's not just that we render objects that we haven't rendered in the first pass. It's also that we update the visibility status that we are going to use next frame in this like first pass, right, for all of the objects, regardless of whether we've already rendered them or not, using the depth pyramid. And so this is an interesting setup. This essentially means that if your camera is stable and if your set of objects and positions are stable, then you record perfect information about visibility, and then on the next frame you're going to render basically all objects on screen. You're going to build a perfect depth pyramid, and then you're going to render nothing in the third pass. But then if something changes, then there is some imperfections about the depth pyramid because you haven't rendered some objects because, for example, you think they might be invisible. And maybe there's some occlusion things that don't work, etc. But the existence of this third pass kind of corrects for the fact that maybe you haven't rendered some objects that were that should have been rendered. So for all of this to work, you need to do 2 things. One is you need to have 2 passes for rendering things. And so the first pass here does not do occlusion tests, and the third pass rather does the occlusion tests. So all of this is in the culling shader. So we call this third pass late pass. And so this is not the shader that's used for rendering, this is the shader that's used for culling. And so you can see that in the second pass, when occlusion culling is enabled, if the object passes basic checks like frustum culling checks, then we do occlusion tests, which is this code. And then in the late pass, regardless of whether we have rendered an object or not, we are recording this visibility status for the sort of last, for the next frame. And also the conditions for rendering, this shader runs twice. It runs before the first pass and before like the third pass. So the conditions for rendering an object are as follows. Like it passes all visibility checks and also either wait. Wait, what? Hold on. Is this condition wrong? We need to look at this code carefully because we're going to be copy and pasting this code into some other bits and refactoring stuff along the way. So this is like important code. Is there a bug in this code? So, oh, I see. Okay. There's no bug in this code. It's just confusing because it's just confusing. Okay. So in the first pass, if the object was not visible, we are not processing it at all because we know we aren't going to render it. But then in the second pass, we process all objects, and then the condition for rendering the object in the second pass is that we have not rendered it in the first pass, which is correct. Okay. All right, so this code is correct. So we need to do something similar to all of this, but for meshlets. For this to work, essentially, we are going to be modifying the task shader to do similar work where we render twice. We already rendered twice, but when we render the first time, we need to ask, was this cluster visible last frame? When we render the second time, we need to ask, was this cluster invisible last frame? And if so, we haven't rendered this cluster yet, but should we? And if so, render it. And this is where the occlusion test comes in. And then the second thing that we need to do is in the second pass, we need to update the data about all clusters for the next frame. So that's kind of the idea. That's what we are doing today. The first thing that we need to do for all of this to work is that for every cluster, we need a way to look up this Boolean of visibility in some sort of buffer. And so we're going to make this buffer. The way we are going to make it is going to be a little sketchy, or I don't know how to say this. Like, it's not going to be optimal necessarily, but maybe we are going to correct that in the future. I'm reading this code. There's some C++ code that we need to write and some shader code that we need to write. And there is some complexity about this. Essentially, the big problem is this. So we need some way to identify. Previously, we've always worked with draw calls. There is like a global buffer of draw calls, whether they're visible or invisible. And then clusters or meshlets, they were always kind of how do I put this? There was no global identity of a given instance of a cluster on screen. It was a combination of, there is a draw call which has a transform matrix, and there is a cluster number 75 in the mesh. And the cluster number 75 in the mesh can be rendered on screen in a million places. It's always number 75 out of the mesh, but it's a different number of draw calls, right? So essentially we have the draw ID, which is the first thing, and also we need the meshlet ID. What I'm trying to do is, or what I'm trying to see is, there's this weird thing. Oh, is it just global invocation ID? It should just be global invocation ID. We need to allocate a buffer that can essentially cover Yeah, okay. So I don't love the code that we're gonna write, and it's likely that we're gonna replace this code in the future, but for now we need to get something going. So okay. Right, all of this is filled on the GPU. Why do we even have... Okay, got it. All of this is filled on the GPU. So the issue is like this. I want to add something like visibility offset. And it's going to be an offset in like Meshlet visibility. And it's going to be an offset in a large buffer that has space for all clusters, for all draw calls. This is not optimal, but this is what we're going to start with because it's, I guess, simpler. Sorta. But for this to work, we need to fill this guy. So let's just go through this code. Unfortunately, we need to duplicate all of this stuff a little bit. So we need an offset. There's going to be a big buffer, and for every cluster of every draw call that we render, there's going to be a boolean or like a 4-byte integer, probably, whatever, it doesn't matter, in this buffer. The first thing that we need to do is make sure that we can make this large buffer, and for every cluster, for every draw command, sort of indicate what slice of this buffer we're going to use, which is what the offset, which is what the offset is for. But for this to work, we need to compute this offset somewhere. And so for now, we're going to do a bad sort of stupid thing. We're going to compute them on CPU ahead of time. It's going to be a lot of memory. It's fine. Or like we're going to fix it at some point later if this code even works. But this is what we're going to start with. So this must be filled on the GPU because this buffer is filled on the GPU, right? So there is a Meshlet visibility offset, this is a mouthful, that we need to read from somewhere. And really we need to read it from draw call buffer. So this is draws di. The way that you compute this visibility offset goes roughly like this. It's basically a prefix sum for people who know what a prefix sum is. For people who don't know what a prefix sum is, imagine we have 5 or 3 draw calls. Draw call number 1 has 5 meshlets. Draw call number 2 has 3 meshlets. Draw call number 3 has 2 meshlets. So there is a total of, and for us, actually, for now, all of the meshes are identical in how we are testing things right now, but it doesn't matter. So there's a total of 10 things that you need to store here, right? And for this to work, you have to use offsets of 0, 5, and 8. 5 is just 5, and 8 is 5 plus 3, right? And if there was another one, you would use 10, etc. And so the way you compute these numbers is by just summing all of the numbers in the array of counts of meshlets for every mesh, for every draw call rather, from the start. You can compute the stuff on the GPU. It's annoying to do this. I don't want to do this. We're just going to compute the stuff on the CPU in like a very bad conservative manner. And then we are going to hopefully do a nice simpler thing that is going to hopefully work just as well, but maybe this will not be today, we'll see. Anyway, so point of all of this is we need to add this guy here, and then we are gonna compute it on the CPU. At some point we are gonna share all of these structures between the shader code and the C++ code, but for now, you know. Okay, so like this should work in a stupid nope way, like we haven't done anything useful. We're just adding space for stuff to work. Let me switch to this. Yeah, we're gonna deal with the validation error. I have no idea. This wasn't, I literally streamed a couple weeks ago and this thing was not there. I don't know what happened. I don't even know what locally changed in my configuration, but whatever, we are gonna figure it out. I just don't want to spend time on this first thing in the stream. I'd rather do the thing we wanted to do on stream and then figure it out. Okay, so okay, so there's this loop where we initialize the draw calls, and in this loop, we know what mesh we're gonna draw. Because we know what mesh we're gonna draw, so we have this complexity, extra complexity, which is that we have level of detail in the mix. When we work on a per draw call level, it doesn't matter because you're treating all of the level of details in the draw call as part of the mesh, sort of, right? So it's the same bounding box, etc. But every level of detail has a different number of meshlets, obviously, right? Now, ideally, like with a properly generated level of detail scheme, the first level of detail has the most meshlets, but it doesn't really matter. What matters is you need to allocate space for the worst case level of detail in the mesh that you want to use. As long as you're doing things like we are doing right now, where we are pre-allocating positions in this large buffer that will store meshlet visibility status, like ahead of time, right? This is like the worst case. Again, it's not perfect, it's not optimal, etc., but it's simpler. And so in a world like this, you just need to compute this prefix sum that I was talking about. So you this is just how you compute the prefix sum, right? It's really, really simple. So meshlet count should be the worst case number of meshlets in every LOD. We can just use the first one. Technically, it is possible that the first one isn't the worst case one, right? Like, you never know. So we can... all of this code will, hopefully, is that true? Yes, all of this code should become irrelevant. So we are just gonna do the stupid thing, which is compute the max. All right, so this way, essentially, the first draw call gets 0 because this is the initial value of this thing, and then every subsequent draw call has an offset that's offset by the meshlet, by the number of meshlets in the worst case number of meshlets that we are going to ever draw in the previous sort of draw call. So that is it. Lots of this. Okay, so we have a lot. So as I mentioned, this is not a great way to do this stuff. We are handling 1 million draw calls, and I guess, is it 1 million or 10 million? It's 1 million. And I guess the worst case number of meshlets is 308, which kind of checks out because 308 times, let's say 90 is 27k triangles. This is roughly however large our mesh is, right? So we need like a lot of data. We are gonna allocate, I think, 4 bytes for everything like this. Where is the is this the visibility buffer? that we use for meshes? I think it is. It's hard-coded to 128, which is a little weird. How much GPU memory do we have? I think it should be enough. All right, anyway, so all of this is like really excessive, but this is what we are gonna start with because it's gonna make it simple. It's gonna be hard to debug this code if this code doesn't work. So I don't wanna like debug this code. So I wanna start with the thing that should work. Yeah. All right, so, I mean, so this is Meshlet visibility buffer. And what we need is Meshlet visibility count times size of. So this is gonna be like a lot. 300 million meshlets times 4 is 1.2 gigabytes. But, you know, I mean, it's what it is. The other thing that we do, can you even fill a 1.3 gigabyte? This is all crazy, but okay. Let's see. I hope things work. If things like, I hope we have enough memory, etc. Like, I hope we don't run into any like weird limits. Again, so this is very suboptimal with respect to memory consumption. But we are gonna rework this later. And the other thing is, it's gonna be a whatever. We'll fix it later. So, one easy kind of way to fix this would be to just use 1 byte for a meshlet. We really only need 1 bit. One easy way to to improve the situation would be to use 1 byte. The issue is, so we are using 4 bytes. I don't know if there's restrictions around single byte writes. I don't know. Technically, we require 8-bit storage. Let's put a pin on this. Now, I have an idea in my mind for how to rework all of this later that is not going to require this, but we are not going to start with this. We're going to start with a very stupid thing. All right, so we have this buffer, and then technically we don't really have to fill it, but let's just like, so I said we are going to use the numbers, the visibility status from the first frame, from the previous frame. But what does the first frame do? Like, you have never rendered objects. What should you do? Well, you expect that everything was invisible because you rendered nothing. And so for this, you clear, this is of U32T. For this, you clear the whole thing. This is 1 gigabyte clear. I hope things work. Oh, by the way, I forgot to say this. If the GPU crashes right now, we don't really have a recourse. What I meant, so Linux, which we are streaming from, doesn't have a super solid GPU recovery strategy compared to Windows, and there's no separate streaming PC. So if the stream ever dies, odds are we've crashed the GPU driver to the point where the whole thing went down in flames, and if that happens, I will try to reconnect as fast as I can, but just be aware that this might happen. I hope it doesn't. Okay. So then the other thing that is true of this thing is that we are going to use this in a task shader, not compute shader. And we are going to read and write. Okay, so, and like this is redundant in the sense that this is all happening in the first frame. We can combine them later. Let's see what happens if we run this. Okay, nothing exploded. So I guess it's okay to just fill a 1 GB buffer and no big deal. Okay, we're only doing this. This is all stupid and efficient and stuff. We don't even need to do this because the culling scheme is conservative. It actually does not matter. The final result on screen should always be correct no matter what the contents of this buffer is. And whatever the contents of this buffer is, we are going to correct it at the end, sort of like next frame, or at the end of the current frame. So like it actually doesn't matter. We actually don't care about filling this. I think the reason why we do this is because Vulkan complains about some barrier stuff, which is fair, and there's probably maybe like undefined behavior of some sort technically in the API, but like actually this is stupidly redundant. And the same applies to the thing that we did before per draw call, but like this is a 4 MB buffer and this is a 1.2 GB buffer, so there's a little bit of a difference in scale. But this is fine. This only happens in the first frame, so it's not going to affect our performance. Okay. So then, now that we have this buffer, the next thing that we need to do is we need to have 2 versions of the task shader. We had this weird problem with an AMD driver. I actually checked, and the current AMD driver that we use like doesn't have this issue, and neither does the latest AMD driver. There's like too many AMD drivers, so it's hard to know. But we've hit this bug. I validated like 3 years ago. I validated that this bug still occurred on Windows on AMD drivers, like mid last year. I don't remember when. On latest drivers. I don't know if, and then I reported it again, and maybe it has been now fixed, which is why it doesn't happen. Or maybe both drivers that I use are sufficiently different that the bug never happened to them in the first place. It's hard to know. But the easiest way, so what we need to do is essentially we need to have 2 versions of the shader, because we have these 2 passes, and as you saw, there's some conditional logic on whether we need to do like some extra work around updating all of these bits and whatnot. So like like there's 2 ways to do this. One is you pass a boolean in your uniforms. One is you use what's called specialization constants in Vulkan, and then compile sort of 2 versions of the pipeline. We're just gonna put the boolean somewhere in global state because we have it now, and then we'll see if we need to revise this later. Oh, and the other thing that we'll need to do is so to perform level of detail, to perform occlusion culling, we need like a bunch of extra state. We need the dimensions of this pyramid depth buffer, which are not exactly the same as screen dimensions. And also we need linear, which I don't remember if we have in globals. We do. Okay, so really what we need is we need this. And then we need occlusion enabled just to like be able to toggle this, and then we need this late boolean. I need to clean up all of this, but it doesn't matter for now. So I think with this I was talking about this last time, how we have a little bit extra space left in this global struct, but not too much. So now we still have 16 bytes left in this technically. Okay. So, great, something doesn't work. Oh, but we'll need, oh no, this is fine, okay. All right. I can just steal this from here. And then I can steal this. I guess it's zero initialized. Okay. So I think we're done with most of the setup on the C++ side. The only other thing that we need to do is we need to actually pass this buffer to the task shader, because we are gonna use it. So we have an interesting way that we are doing buffer binding, which is that the indices are the same between all shader stages, which is why I have to put it at like index 5. Oh, and I'll have to have this guy as well. Okay, so really I should do this, and then these are 5 and 6, and this is not draw visibility, this is meshlet visibility. Maybe this is too many changes at once. Again, the issue is it's going to be hard to debug all of this if it goes wrong. So there is a problem with making too many changes at once without like actually testing them. But let's see if it's okay. All right, so we added meshlet visibility buffer and depth pyramid to the task shader. This means that whenever we render with it, which is this pipeline, we need to pass them. So here we are passing, so this is 0, 1, 2, 3, 4, and we've added 5 and 6. So we've added the meshlet visibility buffer, and we need to pass in the depth pyramid sampler, which I don't remember how. Let's look at, okay, this is how you do this. And there's going to be some barriers probably that we are now missing or mishandling or whatever, that hopefully hopefully the layers will tell us about, but if not, we are gonna have to chase down ourselves. All right, what else? So then the other thing that needs to happen is that we need to pass in this late boolean. I actually wonder where. Oh, right, because okay. So we already run this function twice, so we already have this boolean, so we'll just pass this boolean. And all right, so hopefully once we run this, nothing explodes and we see the exact same result as we did last time, which will mean that we, except for some synchronization, maybe validation errors, which would mean that we can actually write the shader code. So nothing exploded, and we get 0 validation errors. The latter I find very suspicious, because there's bound to be something. There is like bugs here with synchronization. It's unfortunate. I'm reasonably sure that we enable synchronization validation. Yeah. So it's hard. Like I need to double check that the build configuration is right, etc. It is suspicious, to put it very mildly, that we are getting 0. We aren't transitioning like, oh, we aren't using the meshlet. We aren't using any of the 2 new. Okay, maybe this is not suspicious. Okay, I think once we start using these, we may get validation stuff that we are gonna have to fix. Okay, So no, this is right. Okay. So I think we are ready, more or less, to do the thing. The only, the one thing I want to do is I want to move this function to a separate header. We don't have a common header. Let's create something like math.h. I guess there is no pragmas for, all right, so let's just move this guy here, and then include this, and then hopefully things still work. All right, so I think we are broadly ready to start actually writing. Like, all of the things we've done so far were just like setup. We don't know if the setup was correct because we can't really validate any of that. But the code that we've written may have set up everything for success, and we're gonna find out. So the two I don't remember how we did this like several years ago when we were doing this for draw calls. Two-pass schemes are tricky to, because the content of the previous frame sort of matters for where the work gets executed. Like, it doesn't matter for correctness as long as you get the algorithm right. But what if you get the algorithm wrong? How do you debug this? Well, to debug this, for things to go well, so on the first frame, we clear this buffer with zeros. This means we say nothing is visible, which should mean that in the first pass, with the correct implementation of everything, we render nothing. If we render nothing, the second pass in the first frame should render everything because we didn't render things that were visible in the first pass, and it should update the visibility status with ones where appropriate. And then on the next frame, what should happen is things go correct, as in we read the visibility stats from previous frame, etc., etc. But so like the first frame is crucial in its behavior, but it's going to be hard to debug this if things go wrong, because it's going to be hard to, like, we can't step through the code for the first frame that's running. I don't even have render doc installed, but even if we had render doc installed, like, it's tricky to debug stuff like this. And we have 1 million meshes and this giant gigabyte buffer, like, it's hard to debug this stuff. So we're going to try very hard to just get things right, so that we don't have to debug this, and then maybe we fail. I don't know. Okay. So how do we do this? Maybe let's start by copy pasting some code, and then we'll think about this. So what we do in the draw call shader, which I think is still correct to do here, is this. So in the second pass, if the object is visible and we are doing occlusion culling, then we are doing occlusion culling. So we're projecting the sphere, which we already have here, because the nice thing about this is that whatever work, and we encountered this last time, whatever work you do for Meshlet versus the draw call, like, it's very similar if you use the same. We use bounding spheres for both, so it's the same. So like, once you start doing some of this, you already have a lot of things set up in the right way to do the rest of the culling. And this is the situation that we're in. Oh, the other thing that we need to do, we don't have this P00, I don't think. Now, all right. Oof. It would be nice at some point to try to figure out to refactor this to like to be better. It's a little annoying that we have this divergent setups between things. But okay, so this will not compile because we don't have extra projection parameters. Yeah. This error message, this is a named structure, I think, right? This error message is bad. Anyway, thankfully we don't work on the compiler that produced this message, so technically this is just this. So maybe let's just do this. Right, and the function is in the math header. Okay, so in the second pass, we are now doing occlusion culling and updating the visibility status. Okay, so that's the first good thing. The second thing we need to do is, in the second pass, we need to always update the visibility status for the next frame. Right. This was important, but let me try to get this right, and then we'll see. So then I kind of need meshlet visibility index, which is gonna be, so we have this offset plus MGI probably. Okay. So then all of this doesn't matter. So if we are, so then we need to write this boolean to this buffer, and we do the same here. And I guess booleans have to be cast to stuff. I'm gonna cover the valid thing in a sec if this actually works. So meshlet visibility index visible 01. Okay, so now we are writing to this buffer and we are reading from the depth buffer in the second pass. The thing we are not doing yet is hold on, something is wrong. I forgot about the thing, I think, or not. Hold on. Yeah. Okay. I forgot about one thing. I was hoping that I wouldn't have to do the one thing, but I have to do the one thing. That's a problem because we are halfway through the shader code. I don't think there's going. So for now, we're not using this stuff. We're just doing occlusion culling in the second pass of individual meshlets against the buffer. It would even work, sort of. It just would be kind of useless. Let me run this and then we'll see. Okay, nothing broke. I find it very suspicious that we are not getting validation errors right now, but what else? There should be synchronization and validation that we're missing. Okay, so there's a thing I forgot, which is unfortunate. We need to render the objects 3 times, I think. We are only doing this 2 times. I think we need to render them 3 times. Mesh shaders are not supported in render doc. Yeah, see, they might be supported in the pass-through sense, like maybe you can't debug the invocation, but you can still look at the data surrounding it. But yeah, okay, so we have a problem. Which I forgot about. Which is a little annoying. I think we'll need, okay, hold on. Yeah, there's a problem. So there is a problem which I forgot about. To resolve this problem, we'll need the third pass. This is annoying because we'll have to change a bunch of other code to be able to do the third pass. So here's why we need the third pass. Or maybe this is not, hold on. No, yeah, of course we'll need the third pass. Wow, this is a weird interaction. I haven't thought about how I'm gonna resolve this. So, the way these two passes are set up right now is I was talking about this, where we first render the objects that were visible last frame, then we build a depth pyramid, then we render all of the objects, and then we update some stuff. So let's say that for occlusion culling to work, in this first pass in the steady state, meaning the set of objects and clusters and triangles and whatever that were visible last frame is the same as it is now. You need this pass to be, it doesn't really matter how many things you render here, if things are set up, like the rendering will be correct, but you want to try to render as many objects as possible that are visible in this pass, because otherwise your depth pyramid is going to be partially full, and then it's going to have poor culling efficiency, and then the occlusion culling will just not work very well. So for all of this to work then, in the first pass, to render all of the, enough of the visible stuff, but not too much, in the sense that if in the first pass you render the entire scene, then your occlusion culling from this depth pyramid is perfect, but then you've spent so much time in this first pass, then why are you doing all of this? So for this to work in the first pass, when we render the visible objects, the objects that were visible in the past, we also need to render the clusters that were visible in the past. But what this means is that there's objects that were visible in the past with clusters that were not visible in the past but now are. So there is a problem here. With the stable camera, maybe the problem isn't a big deal, but basically there's this matrix. So of 2 by 2. Here was object visible. It's a Boolean. So object was visible. And object, is it a 2 by 2? Was invisible. And then cluster was visible. Cluster is the same as meshlet. Was invisible. So previously we didn't have to consider the second dimension, so we only had 2 passes. Now there's technically 4 states. And we are only dealing with visible clusters, right? So, so if the object was visible and the cluster was visible, then we really want to draw this in the first pass. And then we want to draw all of the other stuff in the later passes after we build up the occlusion pyramid and stuff like that. So the issue is this. The issue is that there is a case, if the object was invisible, then our outer sort of draw call level culling scheme will render it in the second pass. And so, I say pass 3 above because pass 2 is like building the pyramid, so I'm gonna say pass 3 here. So here there's no issue. All of this is good. So the issue is there is a case where the object was visible and the cluster wasn't visible last frame. Because the object was visible, we are not even going to draw the object itself in the third pass because our culling shader for draw calls says, well, the object was visible, so we're going to draw it in pass 1. But the objects that were visible last frame are going to now have to be rendered twice, split in this manner, and only when occlusion culling is enabled for clusters. Once in the first pass and once sort of after the pyramid is built. And if we are not going to do that, then there is a risk where the object visibility status doesn't change frame to frame, but the cluster visibility status does change. Say the object rotated a little bit, and so now some clusters, we are not rotating objects, so like all of this is going to be hard to see, but hard to like know if we are doing things right. But there is this bug, theoretical bug sort of. So what has to happen is that we draw the clusters that were visible in the first pass, then we build the depth pyramid, and then we draw the object again in a special mode where we only draw the clusters that were invisible, but are now visible. Oh boy. Which sucks because like there is this extra bit of state, right, that we need to somehow thread. We aren't even rendering these objects in the first place. And then there's this extra bit of state that we'll have to thread through that is gonna complicate matters. So this is a problem. Now, I'm tempted to first ignore this problem. This is a problem because it affects culling correctness in general case. The reason why it affects the culling correctness is when, or the cases when it does, are when the cluster wasn't visible previous frame, but now is visible. In our test setup, we technically don't run into this. So let's ignore this. This is a problem. I was worried about this, but then I convinced myself in my head that I wouldn't have to solve this problem. But now I pretty clearly convinced myself otherwise. Okay, so this is bad. We are going to ignore this problem for a little bit. Because I think we will probably... I want to get to a point where I see a number of triangles on screen that is rendered that is smaller than what we started with. And say, hey, occlusion culling kind of works. Without the scene changing. And I think I can get to this point without solving for this missing quadrant. However, we do need to solve for this missing quadrant. And there is a few different ways to solve for this missing quadrant, I think. And I don't know how exactly I want to do this yet. There's one big way, really, which is just to draw the thing again. But drawing... Like, so the issue is basically this. When occlusion culling is enabled, I need to draw in the second pass. I still need to draw objects that were invisible, that were visible. So like we already have drawn these objects in the first pass, but we need to draw them again in this third pass. But I have to differentiate them. I have to actually skip the clusters. So I have to have this extra boolean. Essentially, I just want to know the object visibility status on the last frame. Maybe this isn't that bad, but it does mean that there's a bunch of really weird conditions that we are going to add to a bunch of places that are going to suck a little bit. Essentially, we are going to have to teach our culling shader to pass the meshlet, the object visibility status along to the task shader, which is doable. If a little annoying, it's not too bad. It's pretty easy. But then the second thing we'll need to do is we need to teach our culling shader to, if Meshlet pipeline is enabled, still render the objects in the third pass, even if they have already been rendered in the first pass. So basically, you have to change the logic in both layers. But okay, I think we actually don't need a third pass like we don't need to change the C++ code. It's just shader code. Okay. I think it's not going to be too bad. We're going to ignore this for a little bit. It is a problem that we're going to have to solve. Let me add a to-do comment so that I don't forget. To-do when Meshlet occlusion culling is enabled. We actually do need to append this second, the draw command if essentially if it only matters if the object was visible. So if this is 1 in late pass, so that we can correctly render now visible previously invisible meshlets if the mesh changes, like if they change status. We also will need to pass draw viz along to task shader so that it can reject clusters that we did draw in the first pass. So it's getting complicated because there's now dependencies between these two sort of culling things, but it's okay. It's not. It's just a few extra. I think it's just a few extra Boolean conditions. So it's not gonna like make the whole thing. It's not going to require more C++ code or whatever. It's just going to add a few weird conditions to the shader that are going to be like impossible to understand. So we're going to have to write good comments first. Okay, anyway, let's keep going. I think it's going to work out. And I think we don't need this yet. I think we can start without this, hopefully. But even if we can't, it's not a big deal. Okay, so all right, so where we are now, with this problem aside, where we are now is that ostensibly, we don't know if any of this code works, but ostensibly in the second pass, we are doing occlusion culling for individual meshlets. We can't see the effectiveness of this yet, for complex reasons that I don't want to explain right now. This two-pass scheme is difficult to wrap your head around because, again, like, things have to... different passes do different amount of work based on what has happened previously. So right now this is not actually useful. Like if you look at the number of triangles, we should see 6.8 or something like that. Yeah, 6.68. I think it's the same number that we had before. But what we can do now is this. So in the first pass, I don't know how I don't know what the best way is to maybe. Do I change the validity bit? It doesn't really matter, I guess. So I don't know if this is the optimal way to do this from the like, ideally in the first pass, we wouldn't bother doing visibility culling. No, this is not right. We still need to do this. This is actually interesting. Oh, this is different. This is saying in the first pass, if the object was not invisible, just don't consider right, which is what we need to do. So essentially in the first pass, we need to mark objects that were invisible, clusters that were invisible, meshlets that were invisible previously as invisible. And ideally, we'd need to skip all of this work. So the difficulty is this, like it's hard to skip work in the mesh, in the task shader, because it's like a compute shader and it ends with emitting, like compute shader semantics make it difficult. In fact, like, so I can't write this code, or maybe I can, but if this code works here, then it works for crazy, weird, complicated reasons that, like, so basically I can't. Let's just say for now, this might not be the most efficient way to do this. In general, we really need to look at all of this code and how it compiles into actual shader assembly, because there is conditionals everywhere here, a lot of them, and there's a question as to how they are compiled, and for different conditionals it's better to like use a real branch versus not. And I don't know if GLSL has attributes for this, but right now it's a little bit of Wild West. Like, this code could be efficient or it could be very grossly inefficient, and it's hard to tell. But so basically what we need to do is we need to say, well, if we are in the first pass and it's the same thing, it's the same condition from the culling shader. If we are in the first pass and the cluster was not visible in the previous frame, then we should not draw it, and then we should rely on the second pass, or like third pass, whatever we call it, to actually draw it. The only issue is I can't place return here, so I would just say visible equals false, and then I don't, like, we are gonna have to look at how efficient this is. Maybe this is enough, who knows. So part of me expects to see black screen right now, as in no objects rendered, and then we'll have to debug this. It's going to be fun. Hey, we did not have to debug this. But also the number of triangles that we render is still exactly the same. So there's two possibilities. So this means we will need to debug this. Something doesn't work, but hold on. One thing that would help, that we should probably do, is we should look at the data that is getting written here. Oh, let's double check one thing real quick. Yeah, okay, all good. So if, now I don't know, how do I put this? Oh, let's do one thing. Let's make, so there is an open question, which is this. We are doing occlusion culling for individual draw calls. We are not doing this for individual meshlets. The expectation is, and I should have talked about this when we started, is that there are objects that are not completely occluded, but maybe half of the object is occluded. And it would be nice to not render the half that is occluded. And this is what we are trying to do now. But I don't actually know how efficient that rejection is in practice. Because as we discussed last time, there's a difference between the ideal rejection rate that you'd expect when you do things at a perfect granularity and doing this at a high level. Here there's an additional problem, which is that we are taking the occlusion buffer, and then we are building a coarse version of that. So all of this is not perfect. Like, we are hoping that we are saving some work that is approaching optimality, but we can never actually approach optimality. So I don't know what I should expect. Let me try this. So because of this bug that I talked about with the 2x2 grid, I'm now hesitant. I don't know what to expect, because really I should fix this bug before fiddling with the code. But let me try to essentially disable occlusion. It's gonna break something, because it's gonna break the, maybe not. 9.36. Okay. Okay. So that's the same. Okay. So I think okay. So temporarily, we are gonna disable occlusion culling for meshes. So we are now rendering 9.36 million triangles. We used to render 6.68 or something. This tells us that this is the number of triangles that the occlusion culling on a draw call level saves us. If we disable that, but we do the same occlusion culling on a cluster level, on a meshlet level, we should expect at least the same amount of reduction, right? But we are not. which means that this code just doesn't work, period. And now the question is why? And I have no idea. Now I need to look at like everything. Like this code may not be activating. Like it's okay. We are gonna have to debug this. Cool. So I'm gonna keep to reduce the problems with this like weird matrix and stuff. I'm just gonna ignore occlusion culling on the draw call level first, and then try to get to the place where we see occlusion culling working like at all with the task shader, and then I can restore that. It's gonna be easier this way. So let me double check the, sorry, I keep alt tabbing to the wrong thing because I keep forgetting. Okay, so let me double check stuff. So this should, essentially I keep alt tabbing instead of switching between tabs and Sublime accidentally. Okay. Is occlusion enabled 1 from the get-go? Yes, cool. Okay, so then when we actually draw, I think this is the only place, yeah. We store this, pass this boolean, okay. And then we call render twice, false and true. Okay. Oh, one thing we should check actually is, let's look at the pyramid. Okay, the pyramid is there. Well, that makes sense because we're rendering everything. Okay, so what is happening right now is that we are rendering all objects in the first pass. Oh, is that the thing where... Yep. Okay. Resolving the bug that I was talking about is actually critical. As I was saying, it's hard to debug this because it's like a feedback system where whatever happened in the first frame affects whatever happens in the second frame. And the hope is that the whole thing stabilizes to like good results. But for this, the whole pipeline has to work well. Okay, resolving our bug with the 2x2 grid, I think is critical to seeing any results, because to get to a consistent state, in the first frame, the object is invisible. Or in the first frame, the past visibility status of an object is it was invisible. So we render, in the first frame, we render nothing in the first pass. We render everything in the second pass. This means that in the first frame, occlusion culling doesn't work because there is nothing in the depth pyramid because nothing was rendered in the first pass. In the second frame, the hope is that we have correctly updated all of the visibility statuses, but not the occlusion statuses because there was no occlusion data. And so in the first frame, we render objects that were visible, which is all of them. Essentially in the second frame, so in the first frame, occlusion culling doesn't work because there's zero data from the first frame. In the second frame, occlusion culling also doesn't work because we render all objects in the first pass, but we don't know which one are actually occluded because we didn't have this data available. I hope this is making sense. And so in the first frame, we do see the depth pyramid updated correctly, but this was done by rendering too much. And then the hope is that in the third frame is the first frame that we actually see occlusion culling performing. However, for this to work, when we render the second frame, where we rendered everything in the first pass, we are expecting to actually update the visibility status in the second pass, in the third pass, whatever we call it. When we do draw call stuff, we actually do this correctly, which is why things work. When we do cluster stuff, this is where the object was visible in the past frame, but we still need to render we still need to execute its task shader, let's put it this way, to update the visibility status. And we are not doing this because the cluster was visible, and so it's rendered in the first pass. Oh boy. So the upshot of this is that if the object was visible in the first frame, right now we are not updating the visibility status at all of any clusters that were involved in it, because we are not even executing the task shader with the correct configuration. Oh, this is because of this. Can we just, wait, is this logic just wrong? Can we just kill this to get around this problem? I'm not sure if this is correct or not. This is sort of incorrect. But hold on. But this means that in the first frame, this is fine. These conditions are going to be impossible to get right. Okay, that still did nothing. Right, but the occlusion test is only in the second pass. Yeah. Okay, none of this works unless we get the outer structure right. Oh boy. Okay then. Cool. This is all terrible. So the reason why we didn't do this up until this late in the project, it's like an obvious idea. Why not do occlusion culling for meshlets? It's going to be great. It's not going to be great. And the reason why it's not going to be great is that it's really hard to get this persistence thing working really well because of like stuff like this. Oof. Okay. I think we just need to fix the boolean thing and then hopefully things will work fine. This is a pain. All right. Let's see. I'm using Ubuntu. This is the Ubuntu 22.04, so the latest LTS. I tried updating to 22.10 and then I had to reformat with 22.04 because my audio was broken, because Pipewire doesn't work for audio for me for some reason. Or like it doesn't work for the microphone, or it had some weird problems. I don't remember. Basically Zoom didn't have audio, and maybe this problem has been fixed since, but at this point I'm waiting for the next Ubuntu release to try again because I didn't like the experience. But yeah, this is Ubuntu 22.04. Okay. Oh boy. Okay, so all right. Let's do this again. This might have to be a two-stream thing at the rate things are going, because I don't know how much work. I was hoping to actually get to working solution by now, but because of this problem, yeah. So what we expect is that frame, let's say 1, let's number things from 1. Early pass renders no objects. Late pass. Oh wait, was I wrong? Hold on. So early pass renders no objects, right? Late pass renders all objects. And then it updates visibility to draw call level. Frame 2, early, we render all objects, right? And then late, we render nothing. This means that cluster level never gets updated with occlusion information. So for things to work, we have to say that in frame 2 and really in all frames, in the late pass, we have to render the objects again. And then we need to do two things. One is if we did not render the cluster, we need to render it to cover this space that's like in the 2x2 thing. essentially this. And then the second thing we need to do is we need to update the information for all clusters, regardless of whether we have re-rendered them or not. Because without this, we're just not getting information at all. Okay, cool. So, for this to work, we need to add yet another thing to... I don't know how I'm gonna commit this thing, because we're gonna break a bunch of stuff. It's gonna be hard to get to a checkpoint. Okay, so late draw was visible. Let's call it that. It's fine, whatever this is. Late draw was visible. So then draw visibility PI, I guess, equals 1. Or I can just, yeah, okay. Late draw visibility. Okay. Now I need to change this condition. If mesh shading path is active, only. Let's ignore the if it was active briefly, although, nah, let's just do this right, because otherwise it's going to be a pain to do stuff. Okay. Things are not really cleanly aligned here anyhow. Alright, so int mesh shading labeled. We are filling things in a very weird order, but okay. This happens every frame, right? I think. All right, so this means, so in the second pass, we need to redraw the thing. So, okay, so this is not too bad actually, this is just this. So in the second pass, if the object is visible at all, then we need to add it even if it was not invisible in the first frame. If we do nothing else, this will increase the number of triangles that we have to render, because we'll render all objects twice. We'll have to compensate for this by rejecting the clusters. By rejecting the clusters. So in the second pass, if late in the second pass, we need to say that if the cluster was visible and the draw call was visible, so this is, I think, mesh draw late visibility, then visible is false. Or it's not visible, it's weird, it's like we need to skip it, but we still need to update the status. So I guess we need to do this like here. Oh boy. No, but we've already, oh God, why? So if the object was visible and the cluster was visible, this means that we have drawn this cluster already in the first pass. This means we should not be drawing it right now, but we still need to update the visibility status without disrupting this flow. This is all bad. Should we just, yeah, valid? No, but if we set valid to false, oh boy. I don't know how I'm gonna commit this code because it's terrible. This is kind of what needs to happen. I don't know if any of this works. It's probably not mesh draw. What is mesh? No, it is mesh draw. Did I rename it incorrectly? No, late draw, mesh draw command. Oh. Oh boy. I see. Okay, it is mesh. It worked. It worked really well. We're rendering half as many triangles as we used to. Half as many as we used to without it worked. Okay. We did do this to do thing. Or it needs to become a comment. It worked. It worked. It worked. It worked. Yes. Thank God. It worked and it works really well. Okay. That was good. So, how do I know that it worked? We are rendering 3.48 million triangles right now. When we disable occlusion culling, we render 9.36. So, right now, occlusion culling is rejecting, or it's leaving 9.36, right? It's leaving 37% of triangles, so it's rejecting 63 or whatever. With mesh shading disabled, we are rendering 6.69, and then with mesh shading enabled before occlusion culling, we rendered something in the same ballpark. So let's say 6.6 over 9.36. So if we do draw call only occlusion culling, we are rejecting 30% of triangles. If we do Meshlet occlusion culling, we are rejecting 63%. Now, we pay some cost for this, right? Our GPU time is actually down. So this is fine. Yeah. And when I toggle occlusion culling, like, I don't see flickering on screen, so I think things work. Although I need to double check that this visibility thing is not, with occlusion culling disabled, I suspect we are actually now less efficient than we were, because we have this extra pass that does nothing useful, so we should fix that. 25, let's try, okay. All right, anyway, so things work really well. All right, we got to a working thing. It is a little bit ugly. There is this whole 1.2 gigabyte buffer problem, which I don't know that we're gonna fix today. And there is synchronization problem. So there is like problems. But I think the code works, and I think the code is correct. This thing is atrocious. Like, I don't know if I will be able to refactor this on the fly, thinking out loud. Let's explore briefly the performance problem. So 10.33 with occlusion culling, 17 with occlusion, without, yeah, 17 milliseconds and 10.33. So we're faster when occlusion culling is enabled, so this is good. We lost a lot of performance when occlusion culling is disabled. Why is that? Well, this is because when occlusion culling is disabled, we do all of this dance with like second render of stuff, but we gain nothing from doing that. I think it's gonna be enough to say this to fix this particular problem. Wait. Now when I'm disabling occlusion culling, oh, it's because, oof, you can't, oh God. No, that's actually surprising. Hold on, what? Do we not check this somewhere? I'm getting tired from thinking about this. So with this change, when I disable occlusion culling, somehow we are still doing occlusion culling, which is not, and I think it's because of this feedback again, oh, dear God, where somewhere, is this the change where in the first pass we consult the visibility status? Oh boy. So if occlusion enabled is 0, we're still drawing few triangles. This shader shouldn't. It's kind of interesting how the whole thing works. I don't know off the top of my head if occlusion is disabled. What does this code even do? Do we have some high-level checks for occlusion enabled? Or is it all in the shaders? It's only in the shaders. We should probably not be filling the depth pyramid when occlusion is disabled, but we're probably gonna have to fix some barrier codes. I don't want to do this right now. So how does occlusion work when we disable it? This must be because the data is persistent. And I'm trying to figure out if the data that's persistent is the cluster data or the draw call data. I guess before it can't be the draw call data. Oh, it can, yeah, because here we can correctly say, okay. So this must be the case then, that when we disable occlusion culling, some code here is rejecting clusters based on prior visibility status. And it just is sticky, like we never updated. And I don't know why that is. In the late pass, oh, like maybe this is why, because then we don't draw. Yeah, this is why we never clear it up. This is so freaking weird. Okay, I'll have to patch this here. It's really weird. Globals. Okay, this fixed it. Check is necessary because otherwise, if we disable occlusion culling, cluster occlusion status becomes sticky. Draw calls are always dispatched with late 0, I think. Is that a fair assessment? Maybe that is not quite a fair assessment. Maybe more 4 draw calls that are dispatched with late 0. We never update their call status because they are skipped. It's this weird thing where if we render an object in the first pass, then we still have to render the object in the second pass. But if occlusion culling is disabled, this is what I was trying to do. Like, if occlusion culling is disabled, I was trying to not do this, because doing so creates the performance problem. But if I do this, then I am creating the correctness problem, because these checks have to be synchronized. It's all very confusing. Alright, the code works now. I'm reasonably sure it's correct, but there's so many conditions that I don't actually know if it's correct. And there is like the efficiency problem with 1.2 gigabyte buffer. How are we gonna do this? I wanna see if I don't wanna, like, there's problems with this code, right? But I'd like to get to a checkpoint so that the code can be committed, and then we can have another stream at some point where we make things better somehow, by like cleaning all of this up, or whatever. Now, I'm reasonably sure this code is correct, so I can commit it. It's also pretty inefficient from the memory perspective, which is not nice. So I'm wondering if what I should do is simply switch to bytes for storing visibility data, and if that works, I can commit this. Now, there is a better way to do this, but for now it's good enough. So maybe a to-do comment would be fine. Unit 8? No, Unit 8T. What is it? Whoa. What? So shader 8-bit storage. Is this the... Are you actually kidding me? Is this the thing where if I do this, then every access to this... Uh-huh. Well, that worked. Let's do this then. Hold on. So I want to commit this like this. It's not pretty, but then I want to have separate commits that clean it up or improve it. So I think this is correct. And then maybe we're going to spend 15 minutes cleaning things up to the extent that we can do this in 15 minutes, and then we are going to do the rest in some future stream. The synchronization thing is bothering me. Like, we should have had to change the synchronization code. We didn't have to do it. This means there are bugs because there is things that we aren't doing for synchronization, I think, that would have been necessary otherwise. So there's like maybe correctness problem with synchronization. But I think there is no correctness problems outside of the correctness problem synchronization. It's hard to test. Ideally, we'd have a setup where we actually vary camera position and object orientation so that we see that things work in motion. But I think the interesting property of the system is because you have to set things up. The reason why occlusion culling didn't work in the first place is because we didn't set up, I was talking about this transition, frame 1, frame 2, frame 3. Only by frame 3 things are working correctly. For this to actually be true, frame 1 and frame 2 have to do the correct sequence of operations for things to work. And also when you switch between occlusion culling and enable, disabled, like these things have to get correct for this whole process to work. Because the whole process seems to work now, it puts more confidence, like I'm more confident that things actually fully work, but I'm not 100% confident. And also with this occlusion culling bug that we've just reintroduced and then fixed, ideally when occlusion culling is off, can we make sure everything is processed with late false? Ideally, we change this, like when occlusion culling is off, we need to do less redundant stuff. And I think if we do less redundant stuff on CPU, then maybe we will not have to check like random booleans here. So that would be nice. But we got the code to the correct place. Modulo synchronization. So I want to commit it. And then I want to do damage control. Oof. The good news is the occlusion culling works really well. Like it cut the triangle count almost by half. It didn't improve performance 2x, but that's a separate consideration that we're going to explore separately. Implement Meshlet occlusion culling. It works really well. It reduces the triangle count in one camera frame from 6.6 million to 3.4, was it? So it's not by half, but it's almost by half. It's really good. This code seems to be correct, but it may have sync bugs. It has gross logic in places that needs to be refactored. Occlusion culling, when occlusion culling is disabled, like by default we lost a bunch of perf due to running task shaders again. We patched this issue with like random checks, but it needs to be addressed at higher level. Like occlusion culling needs to pay for itself, and so when occlusion culling is disabled, it's important that you don't actually do work that's only relevant for occlusion culling, at the high level, at any level, because if you do this work, you may be offsetting, you may be tricking yourself into thinking occlusion culling helps, because hey, see, I disable it, like timing is worse, but actually for like you need to be sure that with it disabled you're actually doing things optimally to actually tell yourself, oh hey, the extra overhead of occlusion culling is paying for itself. All right, so all right, so that was exciting. We got things to work. Now we just need to refactor stuff. I committed it, but I haven't pushed it. Oh, and we have this stupid validation error. Let me actually read the validation error, because clearly it's a problem for people. It's saying that when you create the shader module info, then the speary blob in question wants fragment shading rate KHR extension. The issue with this is we aren't requesting fragment shading rate KHR extension. Anywhere. I think what this means is essentially we are compiling the shader towards like, I don't actually know what this means. Wait. Oops. There's a more important problem. Well, I mean, maybe not. There's a problem, which is that we have this new buffer. Oh, hey, let's, okay, in terms of making things more efficient and whatever, so first maybe let's not create this buffer if we don't have mesh shading like working at all. And then the thing we actually need to do is we need to destroy it, which we never did, which is what the validation error on close is about. Okay, cool. So that was easier to fix. I'm just gonna like patch it over the previous commit because this was just an omission. Okay, so let's do this again. So when we are creating, it's interesting that it only happens twice, because we definitely create more than two. It's as if task shader and mesh shader, because these are the two modules that sort of are special. By the way, let's see if the code even works if the driver does not support mesh shading at all. It does not. That's a problem. Oh, in fact, I could have just, yeah. So I have two AMD drivers. The one that's installed by default is the official AMD driver, or the official open source AMD driver for Linux. And the one that we were using was RADV, because only RADV right now exposes mesh shading extensions. I'm pretty sure this used to work before the stream. So now if we run, I can just uncomment this, I think. So it works fine on RADV, but crashes on the official driver, which is not okay. Oh, fill buffer. Right. Sorry. This is. Okay. In fact, we could do this when we first time enable this, but let's just do this. It's fine for now like this. Okay. So this was just a stupid omission. Let's do this again. All right, so this is all good. Sorry, I'm going pretty fast, but I want to get this to a reasonable place in like a small amount of time. Okay, so things work when the driver does not expose mesh shading extension. We use an obscene amount of memory for this visibility buffer, which we need to fix. And then there is this logic problem where this whole thing is like impossible to understand at this point, with billions of conditions, and like it's very fiddly. Like the reason why this thing had to not set visibility to false is that this is the case where the object, this is this extra quadrant. Yes or no? No, this is not the extra quadrant. Well, it's sort of the extra quadrant. But essentially, if the object was visible in the first frame, in the previous frame, we render the object twice now, which we didn't used to do. We render it before occlusion culling, like data is created, and after. The reason why we have to render it after is so that we process the meshlets that might have to be rendered even though we didn't render them, because in this first pass we don't just render the object, all triangles of the object, we only render the meshlets of the object that were visible before. And so we have to render it again, but during this we have to skip the triangles that we have already rendered. And the triangles that we have rendered, essentially this is roughly the same condition as this one. But the reason why I can't set visibility to false here is that even if we are not rendering these clusters again, we have to record an up-to-date visibility status that includes occlusion check for the future frames. So like here skip is a separate thing that affects whether we are rendering the object or the cluster, but it doesn't affect this, right? So this all like is super confusing now. Like there are so many ways. I think this code is correct, but there's so many small changes of this code that are naively like, why are we doing this? Like, shouldn't we do this the other way? And you do this the other way and it will break. So this fragility doesn't make me very happy, but hey, 2x triangle count gains is, it feels worth it. The extra amount of actual work that happens here shouldn't be catastrophic necessarily. Now, it's worth noting, I guess, so we have reasonably large objects in terms of triangle count, even though we do level of detail and stuff. For a lot of small objects, just the fact that you render the object again and in the second pass you discard essentially all of the meshlets, that's a problem. Essentially, there is the ratio for every mesh. You can look at how many clusters are actually rejected for occlusion check. And if there is not that many that were rejected, then the whole thing is actually negative. Like it reduces your performance, doesn't improve it. But if you have dense meshes, then it improves your performance. So that's a difficult thing where ideally we would somehow conditionally say if the number of meshlets in the object is small, like 1, 2, 3, that kind of thing, right? Then it may not be worth it. But this is difficult to do. So I think there's some high level restructuring of this that may be worthwhile to make all of these things nicer. Anyway, let's reduce the amount of memory that we use for this. I don't know if I have energy to do anything else right now. I don't even know if I have energy to do that. Maybe we should just stop the stream now, because things work. There's a lot of to-do comments. The nice thing is it's fresh in my memory, so it's faster to address things right now. The not nice thing is I need a break, and so we're just gonna make mistakes. Like, if I could refactor all of this somehow, that would be nice. This thing is pretty terrible. The one thing I was thinking of before this is that, so we did all of this work without adding shader stages and stuff. We just rely more on the task shader. Now, in theory, we could just do, essentially we could shift the culling. If we have, how do I put this? We went from the place where we didn't have to worry about the meshlet instances, so to speak. So like a meshlet that was generated from a given draw call in a given position on screen, to the place where we are burning 4 bytes for it. 4 bytes is excessive, but if we have to store data for meshlet, then really there is not a reason why we need to use the task shaders in the first place. Meaning the reason why we use the task, or there's a reason to use the task shaders, but it doesn't have to do all of this work. Because like we could run a compute shader that does all of this work with culling of individual meshlets, and then just store this visibility bit, and then just have the task shader that reads the visibility bit. Or there's a way to not even use the task shader in this kind of setup. So if you look at the whole picture of what we ended up with, then it looks kind of weird. In the sense that it's not weird, but like it's not clear that this work has to go in the task shader. The issue though is if you remove occlusion culling from the consideration, then actually it is very, very good to do this all in task shader, because you don't need extra memory traffic, you don't need extra synchronization. It's like the optimal thing. The caveat being on AMD hardware doesn't support task shaders. Like all of the stuff that we are doing with task shaders and mesh shaders on AMD, it's actually all fake. AMD hardware does not support task shaders and does not support mesh shaders. We are going to cover this probably in the next, maybe not the next at this point, I don't know. At some point, we are going to cover this in a stream, I think, because it's part of the optimization story, which we haven't covered too much in terms of the actual hardware mapping. But basically, task shaders are just compute shaders on AMD hardware, and then mesh shaders don't exist. There's a different thing that's called primitive shader, which is different. It is not the same thing. They can be used to implement each other, but that is not to emulate each other, maybe is a better way to put this. But it's not the same thing. Which is to say, on AMD hardware, the fact that we're using the task shader to begin with, I mean, we could have just done it all in compute. Because on AMD, at least on RAD, I believe, the data that goes between task shader and mesh shader gets saved to memory. Like it's not, the hardware doesn't know how to do this. There is no compute. There's no task shaders. My understanding of NVIDIA hardware is there's like actual stage that is actually used. And this payload thing doesn't go to memory. It goes, or there's like a ring buffer and stuff, whatever. However, that works in the hardware. So because of this, it's difficult to, for example, we are going to measure performance on AMD, move some stuff out of task shader, and declare victory because it's not slower. Well, maybe it's slower on NVIDIA. It's hard to know. Anyway, so I'm saying all of this to say that the one benefit, like if we actually did use compute, it could be that this whole thing would be less ridiculous in the sense that it would be easier to structure things such that they made sense. But I actually don't want to do this. The other reason why I don't want to do this, I had plans for this visibility thing that we don't really have time for at this point, I think. Yeah, because to actually test these plans requires well, depending on how I want to go about these plans, because there is a thing that's more straightforward that is easier to do. Yeah, but I don't want to change the whole structure. I had an idea about this thing that I want to test out, and I kind of need the structure to test this idea. So for that reason alone, I don't want to shuffle things around too much. And for that idea, uint8 is also a pessimization kinda. So maybe I don't want to do any of that. Yeah, so probably this means I don't want to touch this code. Now I could refactor conditions, but it's been 2 hours, so maybe we should just end the stream. We got to a checkpoint where things work. We are using 1.2 gigabytes of video memory, which we didn't do before. This is a problem. We are still faster a little bit when occlusion culling is enabled, but it's like not great. But the code does work. So maybe we should stop here, and then we can spend, and then the stream is essentially, instead of improved culling, it's just Meshlet occlusion culling. And then next stream, we can actually do a whole lot of cleanup and optimization on all of this, because we are not running at peak efficiency. We are now running at peak triangle count efficiency, I think, in the sense that it's hard for us to do more culling steps that significantly reduce triangle count that we actually do submit to the GPU. Like, we are like really good from this perspective. But how much time do we spend on each triangle, or how many milliseconds, let's put it this way, or like nanoseconds or whatever you want to call it, do we spend on each triangle? That can be improved greatly for hardware efficiency reasons, and also for, like, it's probably not a great idea to be using a 1.2 gigabyte of scratch memory. A lot of this is like, let's actually look at how many draws do we render. Do we say? I don't think it says. It doesn't. There's somewhere else there's a number, which is how many draws we oh no, I don't think we compute the correct. Like, it's hard to know how efficient we are in like numbers, but I can tell you we're not that efficient. And this happened as I converted things to mesh shaders, and then we implemented all of this other stuff. And like, essentially, we are now really good at outputting a smallest number of triangles to the rasterizer. So we are good at reducing the workload there, but we're not actually good at feeding it efficiently. And so this is what we can focus on in the future. And part of this is gonna involve reworking this thing, and maybe cleaning up this whole thing, and this check should be outside and all of that. All right. I think that's the only thing I want to do right now, just to see, because maybe it's super easy, and that will allow us to do things a little bit more sort of nicely. So realistically, when occlusion culling is disabled, we don't need we do need to render the thing, but ideally we'd want all, when occlusion culling is disabled, ideally we'd want all objects to be rendered in the first pass, culled and rendered. There is no reason to use, ideally also the prior state, the prior culling state, like wouldn't be used. I don't know how easy that is to do. So that's like ideally what should happen. Now there's two problems with this. One is the code might not work with this out of the box. Oh, we haven't fixed the validation error. I'm sorry. It's clear that I'm a little bit tired from all of this. It was a lot of thinking on the fly with no breaks. Yeah, so now if you disable occlusion culling, you get a validation. Oh, it's not even a validation error, it's worse. The heck is that? Oh, what? Oh. Oh boy. Yeah. All right. Yeah. Like the actual pyramid generation is pretty cheap. But we are, for example, we are spending it's hard to know where objects are being rendered. It's like maybe it's not that bad. Anyway, all right. I don't want to mess with this. This needs a separate cleanup stream. So, okay, let me quickly try to fix this validation error business because it shouldn't be there. And then we're just going to end. So, for this, the first thing I'd like to know is whoa, what? Is this even a validation error? As in, like, obviously it's a validation error in that something is printing it. Are we even printing it? I don't think so. Things that we print start with error warning info. This is not a validation error per se, in the sense that it doesn't invoke the validation callback. It just happens. Cool. Well, that's annoying. Is the reason why MD has no primitive shader extension yet for the specific optimization? I mean, I don't think they are gonna do this. I would rather they go. So okay, like there's two things to say about this. One is there is a way to use mesh shader in a way that very closely tracks the specifics of the AMD's primitive shader hardware. Like in the sense that the primitive shader, in a loose sense, primitive shaders are a subset of mesh shaders. I don't know if this is exactly right, but this is close to being right, I think. Which is to say that if you use mesh shaders in a certain way, you're gonna have a more direct mapping to hardware than what we are getting right now. This is the question that we are going to explore in the future. And then the other thing to say is that if the delta isn't that large, then is it worth it building a separate like primitive, a separate vendor-specific extension? I don't know. I think in general, Vulkan vendors are trying, I think, to the extent possible to find common ground between different vendors and expose cross-vendor extensions. And then single vendor extensions are a little bit less just interesting for anyone as far as I can tell. So I think even if, I think the reason why AMD never exposed anything Like with NVIDIA, it's interesting, right? They exposed the thing that I think more directly maps towards their hardware, and then kind of forced other vendors to implement it. AMD had primitive shaders for a while, I think. But they never, I don't know, never exposed it. Anyway, okay, so all right, so this validation, this looks like a Spear V validation error, which is like, which is a problem. Which is a problem because it might be, okay. I think essentially what this is telling us is we should enable support for fragment shading rate. I think, is it a 1.3 feature now? I can't recall. Maybe not. It would be wild if it wants us to enable like an extension of some sort. Oops. So I was trying to, like, it's annoying that I can't. I was trying to find the code and put breakpoint in the code and stuff like this. No, this is not what I need. Sorry, hold on. It's pasted the wrong thing. I want fragment shading rate KHR. Primitive shading rate. Okay. Let me just quickly. None of this talks about that. This was an NVIDIA extension at some point, but I just haven't tracked what happened to it since. Okay, let's look at, I guess, okay, this is the one. So it was made last year, end of last year, right? So this is not in any core version. And then to enable it, you need to pass, no, not this thing. Like this thing, right? Where you say, oh, on the pipeline level or somewhere. So like, what the validation error probably wants us to do is to enable it. The issue is we aren't using this feature in the first place. So something clearly goes very wrong during the shader compilation process. Or validation. Like it's honestly, I'm honestly confused as heck. Do we have disassembler? Cool, we have a disassembler. So let's disassemble. Come on, man. Can I just do? I don't think this will work like this. Okay. Okay. What was it called? Fragment shading? Okay, we have something that declares capability of fragment shading rate. What the heck? Fragment shading rate, it must be the fragment shader, but we only have one. Why are there two messages? I am speechless. Okay, so let's put a breakpoint on the place where we create the shading module, which I think is where the thing is coming from. So this is Okay. Breakpoint didn't work. What is going on, people? Are we building without debugging for something? Is that why? No symbol table is loaded. No debugging symbols found. Cool. All right, so... Right. Okay. Oh, maybe we are now gonna get... Maybe we had validation disabled all this time. Oh, that's gonna be bad. No. Yeah, of course it was enabled. How did we not have symbols? I have so many questions. Okay, so now we have symbols. Okay. I don't... This was like a weird configuration that had... I don't know what... I don't know. CMake man. Okay, so... Oh, this is totally the wrong... What was the actual line? 386. Hold on. 386, not 286. Not having a real debugger is a little annoying. Okay, so not this one, not this one, not this one, not this one, not this one. Wild. So this does not happen during create shader module. Somehow. Even though... Alright, can I put... Is it like using put s or something? Printf, can I put a breakpoint in printf and just call it a day? What else can it use? Output? Let's put a breakpoint in printf and hope. Okay, so this is our hit. This is our hit. So it's not using printf. Okay. I haven't used Linux enough to just remember these things as I do in Windows. If it's not using, it's very reasonable it's not using printf. There is a, what's it called? Is it just using write? So printf is clearly using write, so that's a good sign. Okay. Okay. Yes. Jackpot. Okay, now, okay, it is using fprintf, not printf, but of course the issue is that our validation layers come with 0 debug symbols. And because they come with 0 debug symbols, I was hoping to like look at the code that actually prints this error. And there's no code that prints this error, or the code is... oh boy. There's probably a way to install the package with symbols, but all right. Okay, you know what? Whatever. So we know one of the shaders had this thing in the disassembly. So which shader is this? This is fascinating. This is not even like the mesh shader has fragment shading rate KHR. Is this because there is a dependency of this on that? This is ridiculous. Hold on. So mesh shader. What is clear is that we need gel slang source, and thankfully this is just a single repository that we can check out. But okay, is it just putting a dependency? This is a bad sign. This is ridiculous. So this is why we are getting this, because gel slang puts up a dependency on this thing. Fragment shading rate. But like, it should only do this if we use this guy, which we are not using. I can tell you that. I would expect it to only do this. Okay. Okay, so we trace this all the way back to gel slang, which is good. Let's start by searching for this in hopes that somebody has filed this already, which they haven't. Let's read the code. So we need this. Actually, the search is not okay. All right. All right. I think I can actually finish this because this is mindless work comparing to the work that I was doing before. But I wonder if, so I understand what's happening right now. What's happening is we are building the mesh shader. GeoSlang is like, oh, hey, you're using the mesh shader extension. Clearly, you must want this fragment shading rate thing, which isn't even like, it's an extension that you may or may not use, right? Now, I think what should have happened is that GeoSlang should have only emitted this capability, requested this capability, if we actually used the portion of this extension that interacts with the fragment shading rate extension. So it's either doing this unconditionally, or, for example, maybe it's doing it conditionally in the latest GeoSlang build, but whatever version we have installed on our system doesn't do that, right? So we're going to clone the code and we're going to find out shortly. All right, so fragment shading rate KHR. I mean, they are literally in a test for a mesh shader. So that's a little damning. So shading, let's search for shading rate KHR instead, because it should be more hits. Yeah, okay, so this is just here. So yeah, I don't know enough about GeoSlang source. Like, so it's declaring this variable. I mean, this is probably not the right one. Shading rate KHR. This is geometry shader. Like, this is probably the thing we are hitting, right? So it's declaring, oh, this is insidious. It might be saying, yeah, like it's saying there's a variable which has a field, and use of this field requires this capability. But it is possible that, should we just build GeoSlang and find out? Or is it too much? CMake. I don't know. Too late. Clearly. And all right, let's just build GeoSlang and find out. And it's only doing this for the mesh shader, not task shader, which is sort of like, it sort of makes sense, but so I don't know which one, but presumably this one. And then we'll build Niagara C shaders, Meshlet, mesh, GLSL. And then we need to pass something to this thing. Essentially, this is the set of options, and then we will output to out as PV, and then spirvidis out as PV, and there's our fragment shading thing. So this is not fixed in the latest. When I say fixed, there's two possibilities. Why does it? What even is this? Maybe this is an issue. Maybe they reused. Hopefully, they just reused the same. Okay. This is also like, it is odd to see. We are not even using the NVIDIA extension anymore, right? So any leftovers of the NVIDIA extension, like, they shouldn't be here. I think this might be a small bug in spirvidis, where I assume they reuse the numbers for the output primitives between NVIDIA and the XT extension. Like, it shouldn't be outputting the NVIDIA one, but whatever. This is not a big deal. This is just probably a disassembly thing. Anyway, so I'm assuming it's a bug in the sense that I'm assuming that the use of this extension doesn't actually mandate this. It is possible this is a feature in the sense that if you read the spec closely, maybe, you know. But what I actually think probably happens is that we do use this variable. We just don't use this one. And so, like, it's possible that GLSlag says, oh, you're using this. This must mean you need all of these, even though we don't. But let's actually see. So there was a thing where I can put an actual breakpoint to, probably, unless it's filled somewhere else. But essentially, we are hitting one of these two. We are either hitting this or this. Both of these would add a dependency, or both of these would request this capability. All right, so we need to pass all of this, and then we need to put a breakpoint. Can I just not? Whoa. CP. Can I just do this? And then 814. Perfect. And then 819. And then run. Okay. Is there a loop here or something? Oh, there is a loop. Yeah. So it's going over all of the members. And then it's like, oh, hey, you must be using this thing. So I'm just going to add it. But this is not the case. Okay. So, I mean, I assume this is a bug. Because the alternative is that when you use mesh shaders, you must use this extension that is not even in core. I refuse to believe this is a possibility, so I conclude this must be a bug in GLSlang, where it should not output this capability because my shader never actually ends up writing to this fields. Now, let's double check. I want to report this bug, but I don't know how to do that in the sense that I want to check. Yeah, like they have a test. Oh no, this is not the mesh shader. Yeah, mesh shader built-ins. Maybe it's only happening if you use culling or something like this. This is an NVIDIA mesh shader. The heck? What is even going on here? What? So the test suite has the mesh shader that uses NVIDIA built-ins. And then the output, oh, X mesh shader. Oh God, okay. Okay, so this is good. So yeah, this file is a good example. This is kind of what we are doing. They aren't even testing this fragment shading rate thing, but they have an output. So I think this test just demonstrates the exact problem. It's interesting, this thing declares multi-view capability, which we don't have. But this is because they use view index. Okay. So this is just a bug in GelSlang. I'm just pretty sure this is the case. Let's just file this. Yeah, so it is possible, definitely, that this only happens, and we will test this. This input is interesting because it also uses call primitive ext. So it is probably the case that the access to... This is weird, right? How is... No, like, yeah, this thing is just free. It doesn't enable anything. This is interesting. Oh, yes. This is because if you don't do culling, you don't access the top level variable to begin with, right? Because, well, I mean, there's like other reasons for you to access it, but our... no, how do you... Yeah. This, right. There is a variable for the indices, which is this guy, and there's a variable for other stuff, which is this guy. Before we started doing culling, we didn't care about this at all. Like, this entire array of structures wasn't used, right? Because we only need this. Now we are using this array, but we are not using all fields. We are only using this, right? So the minimum example has to write to some field here, but just not fragment shading rate, right? The expectation that I would have is, as I was saying, like, and this is, I think, the code that is missing. If you look at these guys, right? So they declare the built-in variable, or specifically a field within a struct within an array that is this. What I think GelSlang is probably doing, it's saying, oh, if the top level variable is used at all, we're going to request all capabilities present on any fields. In fact, this is what, there was a loop here, right? That we saw in the debugger very briefly. Somewhere. I swear there was a loop. Member. I don't wanna. All right. This one. Did I imagine a loop? Sure, it was a loop. Oh, right, the loop is here probably. Yeah, this is the loop. So it decorates a struct type, and then it says go over all the members, and then it basically just does it for all members. I suspect, like, it doesn't look like there's a mechanism to skip stuff. I mean, maybe this is the mechanism, but it's only doing this for blocks. Anyway, point being, I think when you don't use the built-in variable at all, then it's not going to even run this code. But if you use it at all, then it's going to add all of the decorators necessary for that to work at all, which includes things that you care about and things that you don't care about. So, anyway. All right. And I couldn't find it based on the search query I had. Now, I don't know if, like, the problem that we hit is technically not specific to the mesh shaders, like it could happen for anything else, but maybe it's the only actual extension where... Oh, hey, is that a thing? No, that's not the thing. That is a separate issue, I think. Right, this is separate. This is somebody was trying to follow the spec to validate this thing, and the spec said that it's an array of booleans, but it's not an array of booleans. This is separate. Okay. All right, cool. Yay. Usage of any fields of is enabling capability of fragment shading rate KSHR, right? Or maybe primitive shading rate KSHR. No, this is the built-in. Okay. Even if I suspect essentially I'm trying to find like the name of the field that is actually should have done this. This guy, right? Even if it's not used, you can see this bug in GeoSlang's own test suite. So this is the right one, right? How do you copy copy location? Cool. Source file uses but does not use field in that array of structures. Despite that, the output for that test starts with so this is the output. I mean, let's just quote this whole thing. Out of these, multi-view and draw parameters are basically all of these are correct except for this one. All capabilities other than and are expected as the shader does fill them. It looks like GeoSlang's the output calls this guy whenever the variable of that type is being written to at all, but doesn't filter out members that were never used in the shader, and as such we get this capability. The reason why this is a problem is that this results in a further validation layer failure or error when loading the shader, assuming HR fragment shading or whatever the heck it's called is not used. And let's cite the error. I don't know where the error was. Too many terminals. I guess we can just... This is the error. It is also disturbing that this error is not actually resulting in the call to our callback, but that's a separate problem. All right, so I will link this to Niagara's repository as we usually do for cases like this. The upshot here is it's not our bug. We can work around this bug by like enabling this extension, but what if this extension isn't available, which it might not even be on my GPU, I have no idea. We can check. It might easily be unavailable. Or it could be available, but it's wrong to, I guess it's available, but it's wrong to request, like it's wrong to enable it because it's wrong to request it from the shader. Like I don't want to paper over a bug by a thing that is like super incorrect. So I'd rather this bug was fixed. And it looks like this error isn't catastrophic somehow. Like it doesn't, for us, it doesn't even result in any breakpoints. Like the thing just prints it and goes forward. So, and that concludes the stream. The conclusion is essentially, so we did implement what we set out to do. It works. It's great. It's super ugly, and there's some efficiency problems, but we are gonna solve them at a later date. Probably next week, timing uncertain so far. And that's kind of it. And I will link this bug to Niagara stream. So that is it. Thank you everyone for tuning in. It's been 2 hours and 49 minutes, so we will just call it a day. If there is like questions about overall process, etc., I think we will answer them on the next stream. Because this is the stream where we'll have to re-examine some of the difficult choices that were made right now anyhow. All right, with that, thanks everyone and see you next time, probably next week.